Good afternoon, everyone. My name is Hu Kun. I come from the University of Chinese Academy of Science. The title of my presentation is Robust and Blind Image Watermarking Algorithm, or Circular Embedding and Bidimensional Empirical Model Decomposition. I'm very glad to have this opportunity to report our research. I will show my presentation in the following aspects. This is my presentation overview, which includes the introduction, algorithm details, experimental results, and the conclusion. Let me introduce the background of this paper. Traditional watermarking algorithm generally used only one algorithm for image watermarking, which is simple and efficient, but poor performance in terms of robustness. To improve robustness, many algorithms combine several traditional algorithms to propose lots of watermarking algorithms. Recently, a powerful tool for processing image bidimensional empirical model decomposition named BEMD has been proposed and studied in image watermarking algorithms. However, some existing image watermarking algorithms based on BEMD still have many problems. Firstly, embedding watermarkings in sub-images may result in virtual black effects, and the size matching between the watermarking image and the sub-images limits the application scope of the algorithms. Secondly, the original host images are utilized in the watermarking extraction processing, which may not be available in most cases. Thirdly, random modifying the IMFs gives the risk to lower imperceptibility and the robustness. More seriously, all of those algorithms are feasible against geometric attacks, such as rotation, cropping, and scaling. To overcome the problems, a robust and blind image watermarking algorithm versus circular embedding and BEMD is developed. The motivation of our research is like this. Hilbert curve not only solves the problem of the size matching between watermarking image and host image, but also avoids the black effects suffered in most watermarking algorithms. Watermarks are embedded in the extreme positions of the first IMF, which enables our measure to produce higher imperceptibility and robustness. The circular embedding strategy increases the embedding capacity and enhances the robustness of the algorithm against the various attacks, especially for large-scale cropping attacks and JPEG compression. Let's move on to the algorithm details of our work. This is the pipeline of our embedding algorithm. For the host image A, it's decomposed in multi-scale representation of IMFs and the residue as shown in the B. After that, the extreme points extracted from the IMFs and the embedding positions are selected in the first IMF. For the watermarking image as shown in the E, it's described by the under transform to increase the security of the algorithm, and the described image is obtained in F, which will be further transformed into one-dimensional signal using Hilbert curve. And then one-dimensional signal is securely embedded in the first IMF at the extreme position as shown in the I. Finally, the watermarking image G is obtained by combining the modified first IMF with other IMFs and the residue. Embedding regions plays an important role in the watermarking algorithm and directly determines the invisibility and the robustness of the algorithm. The texture regions of the image will be selected as embedding regions. Fortunately, BEMD is good at extracting texture information from images or the sifting processing. And this figure shows the number of the extreme points in each IMF of different images after BEMD. We can see that for different images, the number of the maximal points almost equate to the number of the maximal points in each IMF and the residue. Will the number of the extreme points decrease quickly from the first IMF to the residue? In order to find certain number of embedding positions, the extreme points simultaneously appearing at the first two IMFs are finally selected as the embedding positions, which usually located on the texture region and the characterize the texture details. Usually, the size of the host image and the total number of extreme points extracted from the first IMF are much larger than the size of the watermarking image, which enable us to repeatedly embed the watermark signal into the first IMF more than 2 times. Figure 1 shows a host image with the size of 12 plus 12, and the 4 maximal points and the 9 maximal points are detected in the first IMF. Figure B is a binary letter gene with the size of 4 plus 4, and there are net 0 pixels and net 1 pixels. All ones can be embedded in the maximal positions. However, just the 4 zeros can be embedded due to the limited number of the maximal positions. To embed the remaining zeros, the second term embedding is needed. In the second term embedding, the remaining 4 zeros are completely embedded in the host image, and all ones are repeatedly embedded simultaneously. The result after twice embedding is shown in the D, which not only solves the size matching problems, but also further enhances our algorithm against some attacks. This is the pipeline of extraction algorithm. Geometric attack detecting is performed firstly, and if a geometric attack is present, it is corrected by using speed up robust feature. Watermarking image decomposed by BEMD into IMFs to obtain the first IMF, as shown in D. Then one-dimensional signal can be naturally extracted by checking the contributes of the served embedding positions corresponding to the first IMF. To reconstruct the watermark image, the reverse Hilbert curve and the transform are performed on the one-dimensional signal in F. Since the circular embedding scales is adopted, multiply watermarking algorithm in G and H are extracted and will be further combined to the final watermark image by multi-lens strategy shown in I. Finally, we can get the extracted watermarking information. Left figure shows the advantage of image correction in watermarking extraction. Due to the larger scale rotation, the embedding positions are shifted in the larger range, causing important information lost in the extracted watermarking image. Figure D shows the matched feature points between the watermarked image and the rotated image. Figure F shows the detected watermark image of the image correcting. From the result, we can see that the watermark image can be completely extracted after the image correction and the NC value is 1. Table 1 documents more extracted results against viral geometric attacks, such as rotation, translation, scaling. From the table, we can see that the NC value without image correction are less than 0.52 for 3 types of geometric attacks. In contrast, we are pleased to observe that NC value of extracted watermark image after image correction are all 1, which explains that the corrective statements are useful to improve the robustness. Now, let me show some our results. We can see that the NC values are all 1s under the text of Xiaochao, histogram equalization, gamma correction, and speckle noise, Gauss noise, GPEG compression, and scaling. It's also worth knowing that most of the PSNR values are greater than 50, which indicates our measure also have good imperceptibility. This figure shows the watermarked image and the large scale cropping and the corresponding extract watermarking images. It can be seen that the watermarking images are completely extracted from with 13% correct with different precision, and the NC value are all 1. Even after 50% intermediate cropping and corner cropping, the NC value of the extract watermarking image are still 1s. The reason of our new proposed algorithm can resist large-scale cropping attacks is that the circular embedding scale and the voting strategy are adopted in the watermarking, embedding, and the extraction stages. This figure illustrates the comparison result between our measured with LSB, DCT, and the DWT, and 3 kinds of attacks including Gauss roller pass, fitting, pepper, and salt, and cropping. We can see that our new proposed algorithm have better performance than DWT, DCT, and LSB against the pepper and salt noise, cropping, and Gauss roller pass fitting attacks. For example, the NC value are all 1s for Gauss noise attack and cropping attacks. For pepper and salt noise attack, our measure also obtained better extracted results. Compared with the 2 BEMD-based measures, our new algorithm obtains better performance and has much higher NC value and various attacks. For Gauss filter attacks, 20% cropping attacks, the NC value of our measures are all 1, while the other measures obtained lower NC values in comparison with our measure. Compared with the full Hilbert measures, our algorithm has silent advantages and 19% of attacks. Most NC value of extract watermarking image by our algorithm are all 1. Our algorithm has strong ability against the GPEG compress, Gauss noise attacks, image fitting attacks, cropping, and geometric attacks. Although our algorithm has offered very satisfactory results, it still has a limitation when the host image is containing loss texture regions. If the host image contains a large polite region area, there will be less texture area to be embedded during watermarking and binding, which will give rise to lower imperceptibility and less robustness to viral attacks. We will explore the new node embedding scales to overcome this limitation, which will not modify the host image and don't rely on the texture complexity and the host image as much as possible. Finally, our paper can be summarized as follows. A large number of experimental results and comparisons with the previous algorithm has confirmed that our measure can be obtained higher in perceptibility and robustness and different types of attacks, including image processing attacks, viral noise attacks, image enhanced attacks, and especially the challenge geometric attacks. And that's all. Thank you.